So first let me thank the organizers for asking me to give a talk, and especially Thore for insisting that I give a talk. Though I was very hesitant in the beginning because I didn't know how to combine what I'm going to tell you today with fine grained. But actually I could have given a different title to this talk. Rather than saying lossy kernelization, I could have called it finely grained analysis of kernelization, and that would have been perfectly valid title to the talk. But I on purpose left it as a lossy kernelization because it's the loss which I want to emphasize in this talk. So I'm going to tell you a story which goes as back as 1988, 89, and then we will see how the world looks like in 2015. So this is a dawn, and this by dawn I mean dawn of parameterized complexity, 1988, 1989. By the way, parameterized complexity is much more older than 1988 and 89. But those were called parameterized algorithms because you don't need, as Grohe says in his book, you don't need any complexity theory to do algorithms. You just do algorithms. It's just that you need complexity theory when you hit on the wall and say you cannot do something. And I guess in late 86, 87, a lot of nice algorithms were coming out from the graph miners, and probably Fellows and Downey thought, why not dominating set and independent set has such kind of algorithm as for other problems like vertex cover, feedback vertex set, cycle, path, and all this. And probably that is why the genesis of parameterized complexity started. So this is a dawn. It is as old as 1989. Okay. Now what I'm going to do in this talk, my talk is all about kernelization or polynomial time preprocessing or mathematical formalization of polynomial time preprocessing. And so let me give you a very brief introduction to the definition of parameterized algorithms as well as kernelization. And it is on purposely put on the first slide and second slide because I will change these definitions towards the end. So please have a look. So what does fixed parameter tractable algorithms are? It's basically, they are primarily, when it was defined, it was a decision version of the problem. You had to give an n and k, and typically you are trying to design an algorithm of form f of k n to the power big O of 1. So basically this is basically uniformly polynomial time algorithm, as Daniel had told a long time back. So we could also think of this as this is basically uniformly polynomial time algorithm rather than polynomial for every fixed k. Okay. And these were of called fixed parameter tractable algorithms, and two of the examples on purposely put because we will use them as an illustration throughout the talk is like vertex cover, which all of you know is basically your graph and you are looking for k size vertices which intersects with every edge. And what is path? Basically you are looking for path of length k in a graph. Now what is kernelization is, and this is how we have been selling to all grant proposal, getting lots of money and doing good things, is that it's a method for everyone. And what does it mean by method for everyone? Basically it's a polynomial time algorithm, and it takes an instance I comma k and it outputs an instance I prime k prime with the property that this is an yes instance if and only if this is an yes instance, and we have a size bound on what do we mean by small. So the reduced instance has what you call size bounded by the function of the input parameter, right? So basically it's a polynomial time transformation that transforms any given parameterized instance to an equivalent instance where the size and the parameter are bounded by a function of the input parameter. Okay, formally basically this is it takes an input x comma k, runs in polynomial time, outputs another instance of the same language, and x comma k is a language if and only if x prime k prime is in the language, and size is bounded by function of k. Now the size bounding function is also referred to as kernel for the problem, or the size of the kernel. And now when do we say that problem admits a polynomial kernel? If you're able to come up with a polynomial time algorithm which gives you an equivalent instance, but the size of the reduced instance is bounded by a polynomial function of k. Now this was the definition of this, and let me give you most trivial example for kernelization. Most of you have seen it, but please see it once more. So I want to give you a kernel for vertex cover. Don't worry, it will not take much time. Okay? So if there's a vertex which is isolated, do you need it in vertex cover? Absolutely no, because it is not covering any edge anyway. So just delete it. And then this is a great high degree vertex rule, which we will see it all over again later. So what is this high degree rule says? That if there's a vertex which has at least k plus 1 neighbors, then if you are looking for a vertex cover of size k, then there is no way you can miss this. Because if you do not take this red vertex, then you have to pick all these k plus 1 vertex in your solution, but you are only looking for a solution of size at most k, then this cannot happen. So you make the following pre-processing. You delete V from the graph and you reduce your budget by 1. So now you look for a vertex cover of size k minus 1. Okay. And we keep applying these rules until no longer possible, right? And transitivity of this reduction rules implies that whatever we had in the beginning, please mind the word, transitivity of these reduction rules, and I will write down because we'll come back to this later. This will be an important concept which we will need to fix it later, so I have written it down. So it's great, right, that why it is fine. So I applied one rule. I had an yes instance if and only if what I have got is an yes instance. I apply another rule I have got. So by transitivity, if I started with a yes instance, by applying lots of rules, I still have yes instance, and if I started with a no instance, I still will have a no instance because I have proved that each of the steps in between are correct, or they produce an equivalent instance. They never change the answer in between. Okay, so what conclusions can we draw from here? Of course, if by this process G becomes empty and K drops to 0, the answer is, if G is not empty, it means there is an edge in the graph. Then what you say? You say that no, graph does not have a vertex cover of size at most k. You return no. Or in this case, you can return a trivial no instance, right? For example, you can return an edge and a parameter 0. That's a trivial no instance. Or what conclusion can be drawn? Now, rule 2 is not possible at all. It means every vertex has degree at most k. It means if I'm looking for a vertex cover of size k, how many edges can they cover? At most k square. So number of every vertex has degree at most k, so the number of the edges they can cover is at most k square. So outcome 2, if the number of edges is more than k square, I can still return a trivial no instance. Else the number of edges is bounded, number of vertices is bounded, and we have a polynomial size kernel of size order k square. Great, right? Simple kernel, very simple. Okay. But there's a very fundamental theorem or very basic theorem in parameterized complexity is that a decidable problem admits a kernel if and only if it is fixed parameter tractable. So probably we could have also defined the parameterized algorithms by saying that it should admit a kernel of any size. Now, this is where now we come back to 2008 until people were making, people had just few algorithms in 1989 about parameterized algorithms. But by the time 2007, 2008, people had shown lots of problems to be fixed parameter tractable, lots of problems to be polynomial size kernel. For example, what looked like this, like tree isomorphism and all this. We had color coding technique coming in that gave us a bunch of algorithms. Then important separator kind of techniques coming, which gave us multi-Waker, directed feedback vertex set, and all kind of algorithms. So we had many, many more algorithms by the time 2008 came. And the question which people were interested, so let's go back to this. A decidable problem admits a kernel, this problem, if and only if it is fixed parameter tractable. What is the meaning that it admits a kernel, right? The size bound on this kernel is basically the running time of your algorithm. So if your algorithm ran in time 2 power k, then the size bound on this kernel is like 2 power k. So what is your fine-grained question? Which of these problems admit polynomial kernels, right? So that's a very valid question, that now that we have so many problems, we have shown them to be fixed parameter tractable, does the behavior of all these problems with respect to having a polynomial kernel or not same? And we were not able to answer this question we had very little success with this conjecture, with this assumption, but we never had any, systematic tool to go about and showing that these problems, or some problems, do not admit a polynomial kernel. And then in breakthrough, there were 2 papers came in 2008, one by Bodlander, Downey, Fellows, and Hermelin on problems without polynomial kernels. And there was also a paper by Fortno and Santana in the 2008 stock, Infeasibility of Instance Compression and Succinct PCP. And by combining results from these 2 papers, we could show that lots and lots of problems do not admit a polynomial kernel unless the following complexity theory hypothesis breaks, right? That NP is contained inside co-NP/poly. Now, that allowed us to distinguish between problems that admit polynomial kernel and those who do not admit polynomial kernel. And later in 2010, this technique was further refined by Dell and Dieter van Melkbeek, who showed that for lots of problems, if you have a KQ kernel, then you cannot have k to the power 3 minus epsilon kernel. If you have k power 4 kernel, you cannot have k power 4 minus epsilon kernel. So for example, the kernel which I showed you just now in the beginning with waving my hands and telling you, just apply this high degree rule, that you cannot reduce the size of that kernel to better than anything k square with this theory, right? So world in 2008 now with this theory, world started to look like this. We know that lots of problems do not have a polynomial kernel. Some new problems were added to have a polynomial kernel, and we still far away to understand whether some problems have polynomial kernel or not, right? So like multi-baker, directed feedback vertex rate, caudal vertex relation, as far as I know, we still do not know whether they admit a polynomial kernel or not. Okay, it's just a sample. So the world has got refined in 2015 with respect to, this having a polynomial kernel or not. Okay. So what is our goal? We would like to clean this picture even more, okay? Now, what do I mean by clean this picture even more? That will probably have to wait a bit. So first, let's take a detour. Because, what I want to tell you, the new stuff, it was boring for all the people who knew parameterized complexity up until now, but I needed to tell you to take you on this tour. Okay, so what do we write in the first line in the all grant proposal we write on kernelization is that it never hurts to run kernelization algorithm before running any algorithm such as approximation and heuristics. Really? It doesn't hurt? Okay, let's see. And this is the main criticism, or say main complaint which we find, and I will tell you why this complaint has become much more important to be handled now than probably before. Okay, so I'll come to those as so what we are going to tell you that it really doesn't combine well with approximation algorithm or heuristics. For example, what does this tells you? What does the kernelization is all about? I give you an instance I comma k, you give me an equivalent instance I prime k prime, but what are you telling? This has a k size solution if and only if this has a k prime size solution. So now suppose I ran a factor 2 approximation on my reduced instance. Now I have 2k prime, or say 1.98 k prime size solution for the reduced instance. Can we use this slightly larger solution to get a solution for original instance? At least the way we make our transformation, the way we make our proof, we do not have to guarantee. All we have to guarantee is that if you give me an optimal solution to the reduced instance, this algorithm should be able to give you a solution in polynomial time, an optimal solution or a k-size solution for the original instance. But if you gave him slightly weaker solution, there's no guarantee at all. So now, even if I had a great heuristic and I ran some solution brilliantly on this reduced instance, and I want to have some meaningful outcome, like some meaningful outcome, given a solution for this to the original instance, at least this, the definition does not guarantee it. I'm not saying you cannot do it. All I'm saying that this definition doesn't forces you to please do that in your algorithm, right? And we can cheat this aspect of kernelization, and I will tell you that yes, we can cheat later. Okay, so let me put it more mathematically. What it does not do? So if I give you an alpha factor approximation to the reduced instance, there is no guarantee whatsoever about solution for the original instance. And this is the drawback which I want to talk about. Well, some remark. In most practical cases, kernels are okay. Please don't worry. It's just the definitions is broken. How? I'll give you one example. For example, we could just run for vertex cover. I know that if I'm going to run an approximation of factor 2 later, I could probably run this reduction algorithm not with parameter k, but with parameter 2k, and you can show that then it starts preserving solution up to all solutions up to size 2k, and then if you are going to apply factor 2 approximation, things might be okay. But the main so yeah, this is great, it works perfectly fine, but it is, so basically what I want to say, it is primarily a limitation of the definition, but actually it's not only a limitation of the definition. Now just imagine that, let's just pick our favorite problem, connected vertex cover. What is this? So you're looking for a vertex cover such that this is connected. What did I show you in the picture some time back? Connected vertex cover does not have a polykernel.
Use the different markers, I guess.
Okay.
Black.
Thank you. Has no polykernel. Okay, this is what we know. Now, for those problems, I do not even have such an algorithm, right? So forget about running it for larger values of k and hoping to save this. My hope is that if I allow certain relaxation, such that even for problems of this nature, I start to say something more meaningful, right? I want to have, as I told you before, I want to have even finer classification about problems that do not admit polynomial kernel. Now, those are not the only targets of mine. There are much more. But suppose for now we fix our target that I want to have fine line between that world. Then for that fine line in the world, this definition of kernel, that solution goes to solution, seems weak. So we need to strengthen this definition to take care when I say that this problem has polynomial kernel, but it is not exactly what you said as a polynomial kernel, but it loses something. Now, the moment I start to use the word loses something, I need to have a definition of kernel that allows us to lose something, okay? So next 10-15 minutes, I'm going to propose a definition of kernelization, which will help us to lose something, and that help us to lose something will clean that picture even more. And I hope after this, we will have 5 more workers till 2020. That's the whole goal of this talk. Okay, so basically, definition is broken, okay? So let's fix it. I'm going to give you a very rough fix, and I will tell you why it is a rough fix. So basically, what is the problem? So this is how the world of kernelization look like. You have an instance, you output in polynomial time another equivalent instance, yes, if and only yes. And we can also think of this as like optimal if and only if optimal. I mean, that is also, we could think of this normal traditional kernelization. But first, let's just make one simple assumption. Really, do you care in polynomial time where did it map to? Right? Do you care? I mean, if all I can tell you, if somehow I gave you a reduction, that if you give me an optimal solution to the reduced instance, I could give you an optimal solution to the original, then do you care whether in the forward direction it went to yes instance, to no instance? We do not care. All you say that, look, in polynomial time I should be able to pre-process my input. On that input A, I run something interesting. Then from that interesting, I should be able to conclude something interesting about the original instance. And that's the whole goal. If that is the whole goal, then this idea that yes goes to yes, we can probably forget that. Okay. I mean, yes, there are lots of questions which must be brewing in your head. But, okay, so for example, I mean, if we could have a define that, look, I want a polynomial time algorithm such that you give me a transformation, size bound is small, and you give me any C-factor approximation for this reduced instance, I will give you a C-factor approximation for the original instance. That's great, right? So this is, but now, look, what is this definition tells us? That, okay, I mean, if anyway if the hope or idea is that anyway on the reduced instance, we are going to apply some approximation algorithm and going to use that information to get this, then why not allow loss in the reduction step itself? That, okay, on the way when you went there, you lost something, right? What I mean by this, so what I'm going to call, and this is what a rough definition is going to be, what I'm going to call alpha approximate kernel. And what is alpha approximate kernel? That this is my reduced instance. If you give me a C-factor approximation, I will give you alpha C-factor approximation. And please, something important to point is this C could be anything. I'm not demanding anything. I'm not saying that C has to be this approximation, that approximation. No. Any C-factor approximation, I will give you something which is just alpha bad than what you gave me. So if you gave me a great solution, I will only give you alpha bad great solution from you. So C never factors as a part of the definition. It's only that alpha which is part of the definition. So if you give me a C-factor approximation for your reduced instance, then I will give you alpha C-factor approximation for the original instance, right? And so basically all I'm trying to tell that given any solution to the reduced instance, I should be able to tell something meaningful about the original instance. Now there are some issues which is why I have used the word rough version. Basically parameterized problems is about decision version. Now suddenly we have started to mix C-factor approximation, but these are like, starts to becoming an optimization problem. They have an optimization answers, right? And so we need to be careful what these things mean, how these things should be defined, such that whatever I'm telling here starts to make much more meaningful and theoretically sense, so that we can start proving some useful theorems about it. And now the boring part of my talk starts, because now I will have to build these definitions for you before I can show you anything useful to make some mathematical sense. Okay. So now, what are our expectations? Now, basically, I'm going to make a polynomial time algorithm. Okay? I'm going to make a polynomial time algorithm. And so, the way parameterized algorithm, one way to think of a parameterized algorithm, if you notice, is so at least the world of FPT captures P also, right? So somehow it is able to tell us something useful about polynomial time algorithm. So if we are going to build this theory of FPT approximation or whatever this kernelization, it should be able to encompass this world of approximation also in a meaningful way, right? Okay, we will see that in a minute how it will do, and it should also fit with the last 10-year development in FPT approximation which has happened. So, like, I mean, we are trying to provide the way kernel provides to an FPT algorithm. We are trying to provide in some way some notion of kernels for the FPT approximation world. That's one of the common goals here. Okay. So as I told before, approximation is about optimization problems, and most of the parameterized algorithms is built around decision problems, of course, except doing parameterized approximation, right? Because there you cannot talk about decision, you have to talk about optimization. So except that, everything at least we do is about decision problem. Now, so we need a notion of parameterized optimization problems, and we need to build a parameterized complexity around these notions of optimization problems. It should be robust, versatile, and it should be natural. And it should encompass parameterized algorithm, approximation algorithm, and kernelization. Big goal. But before we go, here's a word of caution. So notion of parameterized optimization problem, as I told before, this is a basis for defining parameterized approximation. So it has been defined by Chen, Grohe, and Grober in this paper 2006. And thanks to Daniel, I owe him a dinner, that in his survey also he has defined these things in a very, very meaningful way. And you can do a lot of things starting from those definitions. So we could build everything around starting with this notion of optimization. For regions, I will not explain to you in this talk, we are going to define to you a different definition of parameterized optimization problem, and the definitions which are here and which we are going to tell you, they coincide more or less. So we could have used anything to build this. So it's not that if you use those definitions, our results will fail or other way around. So whatever we are going to tell you is consistent with what is known. This is something which I want to make a point about. So we're trying to build such a framework for approximate kernelization, because that is what our goal is. Our goal is not to solve or something, but it's just that we need something, which is robust enough to talk about everything else. So what is the parameterized optimization problem for us? So it looks like very generally parameterized problem is just this two tuple, right? Sigma star cross n. Okay, so it is good old sigma star cross n, but there's another sigma star, and that sigma star signifies, so instance of parameterized optimization problem pi are as again, it's going to be pair I comma k in sigma star cross n, and this sigma star will represent a solution to your problem. Okay, so a solution to I comma k is simply a string in sigma star, right? So basically, what is this parameterized optimization problem? We can think of this as a function which takes as input a pair, like which is first I comma k, which is parameterized instance, and s, which is a solution, and it outputs some reals and plasma. So this is how we are going to define parameterized optimization problem. Okay, such that, and of course we have some size constraints on the string s, which is going to represent our solution. Okay, and what is the value of the solution? Well, it's very clear, right? This is why we define this function. So value of a solution is basically given this I comma k and s, whatever this function pi maps it to. So for us, any parameterized optimization problem will be a function from sigma star cross n cross sigma stars to real, which also includes plus minus infinity. Okay? Okay. What you want to do in optimization problem? You want to solve it, right? Just as goal. So we also like to solve this optimization problem and want to get as optimal solution as possible. But what is the best possible value means? Best means either maximization or minimization. And so we need a notion of optimum for parameterized optimization problem. What is the meaning of optimum for parameterized optimization problem? So let's give that definition to you now. Well, so for an optimization problem, so now I'm only going to define, so throughout this talk, I'm only going to focus myself about minimization problem, but you can build these definitions analogously for maximization problem. So for a parameterized minimization problem pi, the optimum value of instance I comma k in sigma star cross n is that basically you go over all s in sigma star and size of sigma star is I plus k, and you take min over I comma k comma s. Now, if you pick up your favorite problem, so then what it means basically, for example, if you had a vertex cover, right, in traditional sense, basically it says that look at all solutions, right, look at all solutions which are vertex cover, and you take minimum over that. But we also have k, and that will come to play in a minute. Okay, so this is what will be the definition of an optimum value of instance I comma k, right? So because I defined it first, given a pair I comma k and a solution, what is the value of that? Now, given an instance I comma k, what is an optimum value of that instance? For example, look at a vertex cover. You could have lots and lots of vertex cover. So given a vertex cover, this tells you something. For example, it is the size of this vertex cover. And what is the minimum vertex cover? For a pair and a vertex cover, you go over all which is a vertex cover and take the minimum. So analogous to that, we first defined, what is this? That, okay, given a pair and a solution, you have a value. Now, for this pair and a solution, right, I go over all solution for the particular pair, and I take minimum of whatever my function pi, assigns to. Okay. Okay, so for instance, I comma k of a parameterized optimization problem, what is an optimum solution? It's basically a solution S such that pi I k comma s has the value equal to the opt. So this is what we mean by an optimum solution. Okay, is this 2-3 definitions okay? I'm not trying to build anything completely unnatural. This is exactly, we're just trying to, yes, please.
I don't understand your constraint of the length of S. Why is that bounded by the length of the input plus k? It could be maybe larger, no? Or not?
Yes, done. Can you answer?
It's just for the minimum to be well defined. I mean, you could just as well have bounded it as any function.
Any function.
You just want it to be finite for finite instances.
Yeah, but it restricts your solution space, no?
But then you could have the instance. I mean, here you can change the definition slightly as long as the space of solutions is finite for finite instances. This is really the only thing you care about.
Okay, it should be only finite. Okay.
Yes. Okay, so now let me give you an example with connected vertex cover. Okay, so what is, and on purpose, because we are going to give a good algorithm for this. Okay, so what is connected vertex cover, right? So I just defined you. All of you know it's a vertex cover so that the set of vertices which is a vertex cover is connected. Now I want to define this as an optimization version. So now, so given g comma k comma s, right? So I want this pi is a problem CVC, given g comma k, which is input instance, and s is some string solution. What I'm going to say, if s is not a connected vertex of the graph G, I mean, you should just assign it to infinity, right? Because it is like it's not even a solution. So the value of this object should be infinity. It's like too high. Otherwise, if it is a connected vertex cover, what is a natural way one could define in normal optimization problem in classical setting? Just put, it should not be minimum, it should be just cardinality of S. Sorry, my bad, it should not be minimum, it's just cardinality of S. But now, but if this is what is going to be definition, then what role this K is going to play? Nothing. If this is what I'm going to define as my definition of parameterized problem, or parameterized optimization problem corresponding to connected vertex cover, as infinity if S is malformed and cardinality of S otherwise, then what is the role K playing? Now for that, let's ask ourselves question, what is the role K playing in parameterized algorithms anyway? Well, their role is the following. We basically say that if the parameter value is small, the instance is small in some sense. But when parameter value is large, right? So somehow, I mean, so I would like to use this K to have that connection that when instances have small parameter value, right? Then my instances are really easier to solve. And to do that, what we say that, look, I do not care about any solution if your size is more than K plus 1. I really do not care. I mean, they are not useful for me. But it starts to make sense to me only when the size of the solution starts to becoming less than equal to K, because then I know I can do something with it. Okay? So what we define as the definition of connected vertex cover of G, K, S is minimum of mod S comma k plus 1. So if it is not a connected vertex cover, it is plus infinity. But if you notice, if you had a connected vertex cover of size 50k, it is just going to crop it down and going to assign k plus 1. It's only going to start making sense for this, this definition when the solution S which you are going to propose has size at most k. Otherwise, this definition or this algorithm is going to be blind about any solution which has value larger than k, like k plus 1, k plus 2, anything. So this is how I'm going to define my connected vertex cover. Now, lot of you define something greater than equal to opt, right? You say this is greater than equal to opt. Now notice that whatever may be the value of opt in, if it is strictly less than k, this automatically gets captured here, because if opt is less than equal to k, say log k, then the value of that S is going to be this. Now, I have to tell you that what it means to solve it. So suppose you gave me a number k, but the graph had a vertex cover of size log k. Now, if you gave him g, k, this log k size, what is this going to return to you? Log k. You look confused, Mike.
I'm wondering why you don't say it's infinity if S is not a k connected vertex cover, and just put the k on the first row.
Because there's a reason for it. Okay? Yes. Is that, I mean, you do not want, look, there are bad solutions and there are almost bad solution. So k plus 1 is almost bad solution, but they are not as bad as, okay? So you just want to have distinguish between them. Like, it's just little bad. K plus 1 is just little bad if is what we are looking for k, okay? So that's the main reason, like, okay? To have this distinction between too bad, slightly bad, and good. So for us, the good is anything which is less than equal to this. Now, with this definition, with this definition, if for a pi g comma k, pi, so now if I go have an instance g comma k, what is its optimum value? If it has a connected vertex cover of size less than equal to k, then its optimum value is exactly equal to the minimum connected vertex cover size. And if it is more than k, I don't care. It's k plus 1. Sorry. And if it is more than k, then it's k plus 1. Right? So if it has any solution which is size more than k, then it is k plus 1. But anything less, it is equal to the minimum size solution. Okay? So that kind of captures the notion which is used in building FPT approximation, if my understanding is correct. Because, okay. Now, what is the meaning of pi, the parameterized optimization problem, which is basically means pi, the function, takes blah, blah, and blah, outputs a number. What it means to solve pi, it should output a solution S of optimal value. So this is what it means to solving pi, that given an instance, right, it should output a solution of optimum size. Now, optimum makes sense, right, because given I comma k and this pi, I have told you what optimum for I comma k means. So now you have to make an algorithm which should output an optimum solution with respect to this definition of pi. Now, what is a fixed parameter optimization problem, or FPT algorithm for optimization problem? We say that it is FPT if in f of k in polyn it solves this problem. By solves, it means that given an instance I comma k, it outputs an optimum solution. That's it. Okay. Now, so this is the definition which we started with in the beginning. It was primarily meant for decision version. Now we have changed it with respect to this as solving an optimization problem. Now, so basically solving decision problem amounts to always output yes on yes instance and no on no instance. But for optimization problem, algorithm also has to produce an optimal solution. Okay? And this is analogous to the definition of optimization problems most commonly used in approximation algorithms. Okay. This is not if and only if. All I want to say is that given a parameterized decision problem, you can model it as a parameterized optimization problem, and given a parameterized optimization problem, in most cases you can also model it as a parameterized decision problem, right? And okay, and basically you can have, like, using self-reducibility tricks or something, you can output a solution. So for example, most parameterized algorithms which I am aware of actually outputs a solution. So in some sense, they can be used for optimization problems. So most of the algorithms are also like in this definition, they are also FPT algorithm for optimization version of the problem in picture. Okay, my God. So now I need to define kernels for parameterized optimization problems. All this while was to get to this notion of kernel for parameterized optimization problem. Well, this is not what we want, but let me still. So what is an instance I, k? So basically now I'm going to introduce these two concepts. One is a polynomial time reduction algorithm. So given I, k, it outputs me an instance I prime k prime. And then I have a solution lifting algorithm. This is also a polynomial time algorithm, which if you give him an optimal S prime, it should output an optimal S. Okay? So this is good old kernel in the setting of parameterized optimization problem. Okay? That if I give you this is a polynomial time algorithm which takes an instance, outputs I prime k prime. If you give him an optimal solution, it outputs you an optimal solution for this. Okay? But this is still good old kernel, but in the setting of parameterized optimization problem. Okay. And you can prove this. A decidable parameterized problem pi is FPT if and only if it admits a kernel. So this theorem is still good and it holds. Okay. So what is FPT approximation? So first let us define what is polynomial time approximation for parameterized optimization problem. Well, it's an alpha approximation algorithm. If it run on instance I, k, runs in polynomial times and outputs me a solution whose value is alpha times opt. That's it. Right? Good old approximation algorithm, right? It runs in polynomial time, and I'm only defining for minimization problem. I'm not defining it for maximization problem. So it outputs me a solution S such that pi a, whatever solution I have output by my algorithm is at most alpha times opt. Okay. And what is fixed parameter alpha approximation algorithm? Well, it runs in this time and produces a solution of this nature. So quality of is just that here I have added f of k. That's all that I've done. Okay. So this defines an FPT approximation. Now, okay. So this is what FPT approximation means. Now, what is an alpha approximate kernel? Okay. So what is an alpha approximate kernel? As I told you before, the rough definition, which was good. Now it starts to make sense because I'm going to define this alpha approximate kernel for parameterized optimization problem, not for parameterized decision problem. Then it's an I, k. It maps to instance I prime k prime. And now if you give him a solution S prime, which is C approximate, it has to lift it to alpha C approximate solution to the original instance. Now it makes, yes?
Your problem was that the kernel was not good, was not polynomial. But this function can be very large in K, right?
Which function?
The one that goes back. How are you solving? So you said if the kernel is not polynomial, we should maybe approximate, right?
Yes. So we'll come to that. We'll come to which the solution lifting algorithm. It is polynomial time.
It's not
Sorry. So for me, polynomial in both sense. Reduction algorithm is polynomial and solution lifting algorithm. No. It is also polynomial. Both are polynomial. So it is a good old polynomial time algorithm. Okay. So it's a two polynomial time. In fact, this solution lifting algorithm depends on I, k, I prime k prime, and S prime, and gives you this solution because he has access to original instance, output instance, a solution to the output instance or reduced instance, and it looks up everything and cooks up a solution for you, yes, but with guarantee that it is just alpha bad than what you gave me. Oh. Okay. Now we can prove the following noise. It's not a big thing, but we can still prove this following. For every alpha greater than or equal to 1 and decidable parameterized optimization problem pi admits a fixed parameter tractable alpha approximation algorithm if and only if pi has alpha approximate kernel. So getting a FPT approximation algorithm is all about, if you're trying to get an alpha approximate FPT algorithm for some problem, it is all about getting an alpha approximate kernel in this setting. Right? This is what I want to point out. Okay, cool. This is a nice thing. What it says, pi admits a polynomial time alpha approximate algorithm, polynomial time alpha approximate, if and only if pi has an alpha approximate kernel of constant size. Okay, let's see why this is a really one-line proof. This is probably the only proof which I will tell you, so let me tell you this proof. Okay, if it has a polynomial time alpha approximation algorithm, if and only if pi has an alpha approximate kernel of constant size. What is the meaning of pi has an alpha approximate kernel of a constant size? Well, here's a transformation which runs in polynomial time and outputs this of constant size. Now, if this is constant size, in constant time, I can find an optimum solution to the problem. So C is 1. So if I gave S prime, which is optimum solution for this, what is alpha approximate this thing should return? And S, which is alpha approximate, because C is 1. Right? So I get an alpha approximation for the original instance. Okay. So what did we prove? We proved that if pi has an alpha approximate kernel of constant size, then indeed pi admits a polynomial time alpha approximate algorithm. What about the other way around? Well, it's not hard. Think about it, what it should do. Look, this is a solution lifting algorithm. Whatever solution it gives, it just ignores, it runs this alpha approximation algorithm and outputs it. That's it. So this is what I said, P, FPT, so approximation, FPT approximation. Now things have started to make sense. Okay. So, now that I have set up all this, I have even more finer question. Which of the problems admit which of these problems admit an alpha approximate polynomial kernel? I can ask this question now, right? Which problems admit alpha approximate polynomial kernel? Because, as good old theorem, if you have an FPT approximation, then you have. Now, that's one thing, but where should you go and look for these problems to get an alpha approximate kernel? Of course, the problems which have an FPT approximation. But now let me ask you a question. Does Steiner tree parameterized by terminals has alpha approximation algorithm? Alpha FPT approximation algorithm? Yes, we can solve it, right? Alpha equal to 1. Connected vertex cover. But they do not have a polynomial kernel. So those are also my FPT approx in this setting. But then those are big list of problems for which I could start asking question, do they have alpha approximate polynomial kernel or not? And of course, the problems which are W1 hard, but they still have an FPT approximation. So this could be a route to get an FPT approximation for W hard problems. But all I'm trying to tell you that this is also a route to understand the problems which does not have polynomial kernel and get even more finer classification of these problems, because they are also FPT alpha approximation with alpha equal to 1. Okay. So this is what I was trying to tell you. But let's ask ourselves, let's fix connected vertex cover, and let's ask ourselves what are the right questions actually to ask about these problems, because that is not clear what is the right question to ask. It has a factor 2 approximation, well known from the polynomial world. It means, It means order 1 size 2 approximate kernel. Okay. It has no polynomial kernel, so no k power big O 1 size 1 approximate kernel. So these two scenarios cannot happen. Like, these two scenarios are not interesting because 2 constant, 1 no polykernel. We have shown that before. So we should look for alpha approximate kernel of polynomial size between alpha 1 and 2. Might be, we might hope. But before I go and start showing my results and I want to make 2 remarks at this stage. This notion of alpha approximate kernel is not only useful here, but it is useful in a lot of other places in the world, and the world has been making an alpha approximate kernel for different settings all their life. For example, computational geometry, what is code sets? In some sense, this is what it is, right? I mean, you given an instance, you do something, and you get it to a very closed set, which is 1 plus epsilon approximation, and then you solve your problem. So the idea there is not about the size constraint, but to get some kind of structure there so that it is helpful. What people do in what people do in this sparsification for connectivity and all, you first sparsify your graph, then you go and run your approximation algorithm such that the running time gets improved. So if I have if I will have a polynomial kernel for a problem which does not have a polynomial kernel, and it has some polyopt 1 plus epsilon approximate kernel, then first I might like to do this, then run the good old approximation algorithm and trace it back. So maybe by this, I can actually make the running time of many of these approximation algorithm much faster, because people have done this in sparsifications and the world of that to get a better running time. Okay, so this could serve very well even for not so well studied problem to help us getting a different form of polynomial running time for these problems. Okay, so now coming back to connected vertex cover. I mean, this is what the right question is, and what is the best answer we can hope for? Well, it would be great if we could show that for every alpha greater than 1, it has an alpha approximate kernel of size k power f of alpha, right? So it is half, then it is like some k of f of half, which is polynomial, and luckily for us, we were able to show this. So this is how the world looks like. This is my accuracy. Generally, people write, I'm writing different, 1, 2, and k power big O of 1, 2 power k, and suppose this is, so basically what we show that anything below this, you are in this world of poly k, so it depends on f of alpha, but it's only when you get closer to 1 that you start getting a kernel of size 2 power k, but for anything else in between, you do have an polynomial size 1 plus alpha approximate kernel. Of course, as I get closer to 1, so this, doesn't it remind you of something like p-tas, e-p-tas? So of course we have some definitions of that nature, like polynomial size approximate kernel schemes or EP-sacs, blah, blah. So you can do all those kind of things here based on what you get, what form of running time you get. So all those definitions from the world of approximation gets transformed here, and you have far many more questions than to answer. Running time, size, analysis, accuracy, trade-off, whatnot. So this is what we were able to achieve as our results. Okay, so for vertex cover 2, whenever you see some numbers, it means it is not us. Okay, this is all, because I have just cut the PDF from the paper because I couldn't write it properly here in this small and put it here. So for example, look at a Steiner tree. It has such kind of approximation, and for a Steiner tree Euler partial vertex cover, our main job is to understand what is known before and translate it into the language of our language. So for example, partial vertex cover, Daniel had an approximation, FPT approximation, which can be just viewed as polynomial size approximate kernel scheme. So maybe DL is the first guy to show p-sacs. Okay, so this, but notice one thing which I would like to point out. Look at connected vertex cover. It cannot have factor 2 approximation. It has been proved that it does not have 2 minus epsilon unless unique game conjecture fails. We have shown that it does not have polynomial kernel, but it has such kind of kernel. right? So imagine what I do. Suppose I want to get 1 point, I know that the connected vertex cover has size 2. So maybe if somehow I know that on these instances things are going to be nicer and simple, I first reduce it with say 1.001 factor loss. Then I apply factor 2 approximation for connected vertex cover. And when I translate it back, it is 2 into 1.001, which still looks like 2. Okay, with some computer error in zeros. So this is how you can do this kind of things, right? So like you go back, apply normal approximation, come back. So this is the guarantee, these are the kind of things which is guaranteed by these theorems. Look at cycle packing. The best approximation is log n. Approximation hardness best known is half minus epsilon. We have shown that it has no polynomial kernel, but no, undirected graph, not directed graph. Yes, sorry. But if you want your approximate factor to be 6, we could get k log k square. But if you are asking for any alpha, we could only get quasi-polynomial size kernel, like k to the power f of alpha log k. And I don't think this is the correct thing. It's just that it's a limitation of us rather than this is the truth. So we believe that this should be k to the power f of alpha log k is not. Because if you recall, how did we show that cycle packing is hard? Via disjoint factor. But for that, we were able to get k to the power f of alpha like p-sags. And we were also able to build small theory for showing that even such kind of things are not possible. And for longest path, you can show that even in this, it does not have alpha approximate kernel for any size. No polynomial size alpha approximate kernel for long path. So here is a small chart of what we were able to show. And I don't have time, but let me, so this is how the world starts to look like now. Poly alpha kernel for connected vertex cover, disjoint factor, Steiner tree, cycle packing. These are same. Still open. I don't know what is about min1's t set. I didn't check, but since I wrote, I thought I'll leave it. Okay. But the question is, okay, directed feedback vertex set, we do not know how to get a polynomial kernel. But can you get a constant factor alpha kernel? Like 6 approximate polynomial size kernel for directed feedback vertex set. Maybe that is an easier question. Maybe that's the first thing to try, or something of this nature. Okay, so this is what. So like this, we should try doing some of those things. Okay, I'm not going to tell you about alpha approximate kernel because how these apply reduction rules. I mean, that is bad. So here are problems. Pick your favorite problem for which has no polynomial kernel and try this approach. Okay, that's. If you're asking for open problem, just pick your favorite open problem and try this. Okay, that's, and I told you DFVS and all this. Okay, now what does it mean? For example, 2 days back, Binka has showed that dominating set has no constant factor FPT approximation. So what does our result imply? It also implies, because of this, that this problem does not have any constant factor f of k, approximate kernel. Great. So, okay. Last remark which I want to make is that let's go back to the definition of kernel, not this kernel definition, right? Look, it did not demand you that if I give you a slightly bad solution, you should be able to give slightly bad solution. This notion and notion of the alpha approximate kernel where everything or say one approximate kernel where if I give you good quality solution, you should be able to give me good quality solution. These are two different concepts because there's a problem which we showed, tree deletion set. It has a polynomial kernel, but we can show that it does not have any alpha approximate for any alpha, like where alpha could be just poly k approximate polynomial sized kernel. So I just want to make sure. And the good thing is it is not under co-np/poly. It is under unless p not equal to np. So because of these connections to approximation world and this, now you should be able to show existence of many of these hardness results by different set of conjectures like PNP, FPT not equal to W1, and all this, we do not have to stick to only co-NP/poly or those things. So that's another avenue for people who are interested in complexity theory to build things around this. And I think with all this, I should stop my mouth and should thank you very much.
Are there any questions?
I think it's very important in your slide is when does it go to the K? No?
Yes.
I mean, does it give you a lot of improvement? Because if it goes very fast, then
It does not go very far. I mean, it's like it's 1 over, how much it is? Alpha over alpha.
K to the 1 over alpha.
1 over alpha. Like 1 plus epsilon.
okay.
Yeah.
But it's for connected.
Vertex cover. Yes. It is just.
Okay, you should also say that maybe you want something like this.
Yes.
I mean, if you just improve little and jump, that's just not a good function.
Yes, I agree. So we have those kind of definitions in the paper. All kind of definitions are there, Hostel's, but I don't think I had enough. 1 hour is not enough to set up. Look, I didn't even show you how, like, connected vertex cover example is very simple to show, but I just didn't have time to show to you.
There might be a kind of second order FPT question around. If I saw it correctly, that was a little bit small, but this optimum linear arrangement had some, say, f of alpha times g of k or a k.
2 power k.
Yeah, kernel, right?
Yes.
While the others had some k to the f of alpha.
You mean this?
And yeah.
Yes. It's Euler parameterized vertex cover. It's basically the algorithm of Fellows et al. From Asia 2003, which is basically doing 1 plus alpha approximate kernel of this size. Yeah. So you can re-understand that algorithm as this. So this is what it is. This is why, I mean, we just reinterpret that algorithm as this.
Yeah, my point was just sometimes the f of alpha function is sitting in the exponent of the k.
Yes.
Sometimes it's not.
Yes. So we will call them EP-sax, P-sax, this way. Like the way we have EP-tas, P-tas. So you can define, this is what I'm trying to do. So in the paper we have defined all this terminology. We have given some examples, but it's just that I just didn't have time. I didn't even tell you what reduction rules are. They're cool.
You mentioned transitivity at some point. You mentioned transitivity at some point.
Yes, it will fail. If you do not carefully, it just fails. So you have to have very strong conditions. Yes, Holger?
So just so I understand this correctly. So it could be that you have a polynomial kernel, but you can't sort of recover the solution, so
Yes.
that you wouldn't have a one.
Yes, and there is example. Example, tree deletion set.
Okay.
It has polynomial kernel, but it has no alpha approximate because unless p equal to np. Yes. Huh? Because you may not have a good, as you say, right? The good reduction, like what do you call, solution lifting algorithm.
More questions? Well, I have one, Saket. On that, on your result about long path, the is that conditional on?
It's again on co-NP/poly, but we need the Oracle protocol of Holger Dell and all to and you need bit more, a few couple of ideas to make it work, but it is based on this Oracle communication protocol.
And for your notion of an alpha approximation, could you have alpha be a function of k?
Yes.
Sometimes you need.
You need. So all these things are completely allowed. So this is like alpha should not be thought of as a constant. Alpha is alpha.
Let's think Saket again.